issues. So let's go ahead and get started. So this is a review for approximation algorithms and randomization algos. So lots of algorithms here. To get started, I just wanted to go over like what we're planning to do today. So my goals for approximation is that first we'll just get through like the main idea, because I think approximation has a lot of inequalities and that can sometimes confuse people of what they should be doing. Then we're going to go through one example on job scheduling. But I was hoping just to keep to one example per topic, because I think, especially for the coming test, is going to be super important to just know your fundamentals, really know the course notes. So we'll spend some time going over that. Then for randomization, we're going to review some probability stuff, recall the difference between like Monte Carlo and Las Vegas algorithms, what boosting is. We're going to do a randomized algorithm example, the magnets problem. And again, we're just going to like super emphasize knowing the notes really well, knowing the concepts really well. And at the very end, we'll have time to like, if you guys want to talk about tips, advice, any questions at all. And we'll stop for questions throughout the whole thing. And you can ask questions in the chat, which I'm not sure how often I'll be able to check that while writing, but Nick is here and he can check the chat. And I'll pause in the middle for questions. So let's get started with approximation algorithms, what the main idea is. So by now, I'm sure everyone understands that we have our algorithm. Let's say A of X is the size of our output. So I'm kind of misusing notation a bit. Instead of saying A of X is our output, I'm saying it's the size of our output. And opt of X is going to be the size of the optimal, the best possible solution. Of course, best kind of depends whether you want a maximum solution or a minimum solution. If you have a maximization problem, the best is the biggest thing possible. So you want your algorithm to be as big as possible. So greater than something. It's definitely not going to be greater than the optimum, because that's not really possible, but greater than some factor of the optimum. And we normally use these Greek letters, but I think it can get a little bit confusing because one, Greek letters are just by nature a little bit confusing. And two is that this beta is kind of hiding the fact that it's not going to be like you're greater than 5 times the optimum. There's like no way you're going to be greater than a bigger factor. Beta is going to be usually less than 1. So it's like, I think it helps to kind of picture what it looks like. Beta is something like 1/2, 1/3, 1/5, 0.75, something like that, where you're greater than a smaller amount of the optimum. And this is what you want to show, that you are greater than some amount of the optimum. Scoot that over. But how exactly do you get about showing it? It's really hard to compare the optimum solution, because the only thing we know about it is that it's optimum. Like that doesn't really have a nice structure that's suitable for analysis. But our algorithm does have a structure. So how do you compare something that doesn't really have a structure to something that's very structured and somehow get this inequality between them? So the trick here is that we know the optimum exists. It is some best solution out there. We can find a different bound for it, something that's a little bit more structured. So if we find that optimum is less than or equal to some upper bound, this will help us like insert a little bit of structure into the optimum, that, okay, now we know optimum is bounded by something. And because of that, we can go ahead, this is just math, I'm putting a beta in front of both of these guys. So if we know the optimum is less than or equal to our upper bound, we know beta times the optimum is less than or equal to beta times the upper bound. But upper bound, we choose what it is. We can choose it to have some kind of nice structure. So it makes it a lot easier to compare our algorithm to this upper bound. So the whole point of choosing the upper bound was that this is a lot easier to deal with than this guy. And so if we can just prove this inequality and prove this inequality, these two separate inequalities, which each individual one of those might be a little bit easier to prove, we can get the big inequality we were looking for. So that's how you should kind of think of these. And the first step you should be looking for is, okay, I want to compare my algorithm to the optimum. So the first thing I have to do is there a nice way to bound the optimum first? So that's what this the upper bound is. The minimum is pretty much symmetrical, but let's walk through it anyways, just to keep it in our heads. Since we're looking for the smallest possible solution, our algorithm should be less than or equal to some factor of the optimum. So let's say another Greek letter. But in this case, it doesn't make sense for our alpha to be something like 1/2. Because if we want an answer that's as small as possible, there's no way we're going to be like half of the optimum when the optimum is already the smallest possible. So alpha is something like 2 or 5 or 1.5. The point is that it's bigger than 1. So similarly, if we want to show this inequality, what we can do instead is that, okay, we've got our optimum. It doesn't necessarily have some structure to it. So we're going to find a lower bound, in other words, something that it is greater than. And by doing some math, we just stick an alpha in front of both of those. And this inequality we can prove just by analyzing the optimum and the structure of the problem. And then the second inequality we can do by analyzing the structure of what our algorithm is doing. And it'll be easier to do that because of whatever you choose L to be should be easier to analyze. And then you go ahead, you prove this bound, and you end up getting the big bound you were looking for. So this is like a general strategy. The truth is that maybe there might be a little twist to it. So we're going to go ahead and do an example that has a slight twist to this idea. But the same idea of like using intermediate bounds to help you prove your overall bound is still there. So stringing together inequalities like this is a good strategy. But if you find another way to just prove this bound or prove this bound, you should just go ahead and do that. Okay, are there any questions on like the definitions and setup before we jump into our example? And feel free to unmute your mics. Well, I guess not the whole time. That's a lot of background noise. To ask a question, unmute your mic. Okay, so with that structure in mind, let's go ahead to this scheduling jobs problem. Our goal is to come up with a 2 approximation algo for this problem. So it's a scheduling problem. We have m identical machines. And to visualize it, let's say m is equal to 3. So these are my 3 machines down here. Let me not use that. Let's use this. These are my 3 machines down here. And you want to schedule your n jobs. Let's say we have 5 jobs. And notice they're all different sizes because each job, 1 through n, has a processing time which is greater than 0. So this guy has a processing time of 1. This one has a processing time of 4. And you want to assign each job to a machine such that the make span is minimized. So the make span is like, if you were to start all the machines at once, how long would it take for you to be done with all of your jobs? If you assign, let's say over here we assigned like 100, and over here we assigned 50, and over here we assigned 75 units worth of job, how long is our make span here? Can someone put in the chat or just unmute themselves? Yeah, it's 100. So your make span is like the maximum number here. Because if you ran all of the machines at once, sure, machine number 2 would be done at time 50 and just be done. But you would have to wait all the way until time 100 for all of the machines to be done. So our goal is to minimize the maximum span, which is called the make span. So let's look at these. If we look at these jobs right now, you might be able to like mess around with a bit and think about how to place these and figure out that the optimal solution is that if I place job 4 on its own machine and can place job 3 somewhere and stack these all together, then what is the make span of this? Someone put in the chat or unmute them. Yeah, 4. Because right here, the maximum is 4 across these 2. So that's the optimum. But now we have to come up with an algorithm that just given the jobs, it's not doing anything exponential. We want a polytime algorithm. So an exponential solution would be something like, let's just try out all of the assignments of jobs and see which one has the lowest make span. But we don't want to do that. We want to do something where like we're given a job and we just have to make a decision on which machine we should keep it in. And that's what our algorithm is going to do. Given the job, which machine should I keep it in without having to like try out all possibilities? So let's pause for a minute. Think about that. Think about some good algorithms. And then you can put them in the chat or unmute yourself and we'll analyze that algorithm. So yeah, take a minute.
All right, so I have one for.
Awesome.
Oh wow, Bharat. Well, that was okay. Yeah, that's my idea also.
Did I steal your idea?
Yeah, I mean, she said unmute yourself, but it's cool.
She also said put in the chat though.
But she said she preferred to unmute. It's fine. We can just use that one. Yeah, it's fine.
Awesome. So all of these are great ideas. So it turns out if you sort them and then greedily put your job down, you end up with a 1.5 approximation algorithm. So the algorithm you guys thought of was actually smarter than if you just simply place them greedily. So if you just pick up your job and place it in the machine that's doing the least amount of work, that itself is already a 2 approximation algorithm. If we have time at the end, we'll analyze the sorted version too. It's a little bit trickier, which is why I didn't want to do that one yet. But first, let's just do the greedy algorithm. So the greedy algorithm, which a few of you mentioned, is just, you don't sort them, you just look at the jobs and you place it at what machine is doing the least amount of work. So if we run our algorithm right now, we would take job 1, place it, well, it doesn't really matter. All of these guys have working are 0. So let's just, you could even make it more not more deterministic, it's already deterministic, but you can make it more specified by saying like maybe the first one is sequentially that has the least amount of work, but it doesn't really matter. We would place this one there, we would place this one here. This one has to go into the one that's doing the least amount of work, which would be machine 1 right now. This one has to go to the one that's doing the least amount of work, which is machine 2 right now. And we end up with our make span of 5 instead of 4. So it was a little bit worse, but how much worse could it possibly get? So we're trying to show that the worst it can get is double the true solution. So in this case, like the worst you could possibly get is 8 because the optimal was 4. So just to write down what our algo was, it's basically the greedy algorithm for each machine, place, not for each machine, for each job, place it in the machine. For each job, place in the machine that's already doing the least amount of work. If we want to show that it's a 2 approximation algorithm, what is the inequality we want to show? If A is our algorithm's answer and opt is the size of the optimal answer, which way does this inequality point and what constants are in front of it? Not a rhetorical question.
Like A is less than or equal to 2 topped.
So I heard 2 people say, yeah, it's A is less than or equal to 2 times the optimum. That would make it a 2 approximation algorithm. And from what we saw before, it would be really helpful if we end up finding some kind of lower bound for this, for our optimum. So in other words, it's helpful if we find some middleman quantity that opt is greater than. Can anyone think of some quantities that opt is definitely going to be greater than or equal to? Yeah, someone put in the chat the greatest job, and another person put in the chat the sum of all the jobs over m. Both of those are correct. Let's analyze why they are. So if we go the max over all of our jobs of how much time it takes to process them, so this is like whichever job is the biggest. In this case, that would be job 4 because it has the biggest processing time. Our optimum is definitely going to be greater than or equal to that because there's no way for our make span to be lower than 4. So it's 4 because the biggest job is 4, and then it could potentially be even more if you stack things up higher. So our optimum is definitely greater than or equal to the maximum. The second one is also kind of interesting. You're greater than or equal to the sum over n, which you can kind of think of as like the average processing time. So one way to think of what this means is if we took all of these jobs we have here and we melted them, or like we blended them into a smoothie, what we would be doing is kind of leveling them out so that they would just become the average somewhere down there. That, okay, here's what our average job looks like. If we added up all these quantities divided by how many machines there were, it's like we took all the jobs, melted them into one liquid, and then poured them evenly across our machines. So that's like the most optimal solution possible if we could split up the jobs this way. Of course, the jobs are kind of like concrete objects that we can't split up this way, but if we could, our optimum would still have to be greater than that because we can't actually do that. So this is like if we melted all the jobs into a smoothie and put them evenly over the machines, our opt is going to be greater than that. So now we've got 2 bounds for opt. Let's try and analyze. So the steps here is first find some structure in our optimum, which we did. We found its comparison to the max and we found its comparison to the average. The second thing is to try and find some try and find some structure in our algorithm itself. So one thing to notice in our algorithm, is that if our algorithm's answer is A, it's because there's some machine K that has the largest span, and that span is A. So in this case, in our example, that would be machine 2 is machine K, and it has this largest span, A, which is 5, which is our answer for the algorithm's answer. So let's analyze what the algorithm itself is doing to get that answer. So if the span of our answer is 5, there must have been some last job that was added to make it 5. So let's say that the last job added to machine K has processing time pi. So in this case, our pi is 3. So this isn't necessarily the last job added overall, but it is the last job added to this machine. And it is the one that creates our maximum answer. So before it was added to machine K, so if job 3 wasn't on machine 2 yet, this machine K had its own span already. Let's call that span S. So before we added pi, machine K had span S. So again, going back to our example, S in this case would be 2, because this machine had a span of 2 before we added 3 on top of it. So our answer overall, if we kind of stick all of these together, is going to be S plus pi. So are there any questions so far? Because basically we just defined a bunch of notation to help us analyze our algorithm. And this is a common strategy. It's sometimes like looking one step before you get your answer, so that you have a little bit more to analyze until you get your answer. Okay, so now we have some structure on our algorithm. We had some structure on our optimum. The question is, how do we put these together to compare our algorithm to our optimum? So this is a good time to think for a second. These quantities S and P, what do they have to do with the quantities that we just bounded opt by? Because if we could connect those two, then we could connect opt to A. I don't think I've tried doing an approximation algorithm using, so assume for the sake of contradiction that it's, I think that could work. But in terms of stringing together these inequalities, we're trying to find a relationship between these quantities. So Bharath mentioned that, yeah, we can connect these two by saying that pi is less than or equal to the max j of pj. And the reason we might think of this is because, well, we know eventually we want to connect A to opt, but A is connected to S and I. So if we can connect S and I to these other bounds we have on opt, we can connect A to opt. So that helps with pi. What about S? So S is the span, the lowest span of any machine before you add job I. So we have this connection between opt and the average span of everything. So what do the lowest and the average have in common? Or not have in common? How do they relate to each other via inequalities? Yeah. So we know that the lowest span must be lower than the average. So our span is less than, well, specifically, we know that it's less than the average of all the machines we've added so far. So this would say all of the quantities before we add processor I. But that's okay, because the lowest span before we add processor I is definitely less than the average span before we add processor I, and that is definitely less than the average span after we add all of the processors. So this is after we add all of them. So now we have this one bound on S, we have this one bound on PI, so we can kind of string them together and get that A is less than or equal to the average span plus the maximum job. But we already bounded those two quantities by opt, so we know A is less than or equal to opt plus opt, which is 2opt. And that's what we wanted to show. Are there any questions on this problem? So if you notice, it kind of follows the same ideas from the thing we were talking about before, where you find like an upper bound or a lower bound. But in this case, instead of just finding one, we found two separate lower bounds and kind of stuck them together to get 2opt.
How do we know that the span S is like the smallest one after we remove machine K? How do we know it's still not bigger than everything else?
Yeah, so the reason, whenever you're doing these, the thing you should be looking for is what is our algorithm doing that would give us some bound on these quantities. So in this case, our algorithm is only adding a machine to the thing that has the lowest span already. So for each job, place the machine in the for each job, place it in the machine that's doing the least amount of work.
Okay.
So if you're placing job PI into machine 2, you know that when you were adding job PI, machine 2 must have had the lowest span out of all the machines.
Okay.
Yeah, good questions. Any other questions? Okay. So with that in mind, I wanted to, it's frozen. I wanted to go, that's not the way I want to swipe. Go over some examples you guys saw in lecture. So I don't think it'll be that useful for me to basically like read out the textbook to you. I might go too fast, too slow. It's definitely more effective for you to just go through the textbook yourself and make sure you understand the examples. But I did want to go through like maybe some study tips of how you might do this. So these are just some that I picked off from Diderot of the approximation algorithms you've seen. I would say for each one of them, you should have a pretty good understanding about how and why they work. So in other words, you should be comfortable figuring out like, okay, algorithm, insert name, approximates what problem, and which is it a min problem or a maximization problem? And what are the main ideas behind each of these approximation algorithms? So it's doing something. So there's some key idea behind why it works. There are some steps it takes to carry out that idea. And it achieves a blank approximation. So this is like your alpha beta value. So even though we spent a bit of time like coming up with an algorithm, which I think is super instructive and you should be able to do that, for our oral test, I don't think we'll have enough time to have you sit down and prove something like the job processing algorithm like out loud without writing and showing this to us. So I think knowing things conceptually is super duper important. So understanding the textbook notes, if we gave you an analysis, do you understand why it works? As for coming up with your own algorithm, I would say the main strategy that works for most of the 251 problems is just like doing a greedy algorithm. Sometimes a greedy algorithm with a little twist, like we saw you guys gave really good suggestions that we should do a greedy algorithm, but maybe if we sort beforehand, we can make it even better. So those are like the main strategies for coming up with your own algorithms. Does anyone have questions about approximation algorithms or anything around that topic? Because others are going to move on to like probability stuff and randomization algorithms. Okay, so moving on to randomization stuff. The first thing is don't forget your probability. I think people might get a little bit overwhelmed. They're like, okay, randomization algorithms, I need to know Monte Carlo and stuff, and I need to know how to do these algorithms. But you also need to know like the basic probability stuff. So let's just go over these guys. Markov's inequality. So for the sake of time, I'm not going to ask you guys to like say each one of these, but before I write them down, mentally at least, you should be saying them, recalling them, because like that process is really what's stretching your brain, remembering that, making sure that you can remember what they are. So Markov's inequality is just saying that if you have some random variable x, but not just any old random variable, it has to be greater than or equal to 0, then the probability that that random variable is greater than or equal to some constant times the expected value of that random variable is less than or equal to 1 over c. So that's just Markov's inequality, but I think another way of seeing Markov's inequality, which is useful, is if it's written out this way. Sometimes that can be useful, but just knowing that these two are equivalent, just if you pick a to be c times the expected value, then you just get a different version, which is really useful. Linearity of expectation. So by now you guys have seen it like a million times, but I guess a key idea is, do you need, let's do a little yes or no vote in the Zoom chat. Do you need the condition of independence for linearity of expectation to work? Awesome, so I'm seeing lots of no's in the chat. Yeah, so linearity of expectation works without needing independence between these. So it's the expectation of the sum is equal to the sum of the expectations. So that's pretty useful. Is it true, kind of the same thing, but for products? So if the expectation of the sum is the sum of the expectations, is it true that the expectation of the product is the product of the expectations? Okay, seeing some no's. Yeah, so this is not necessarily true, but it could be true. And yeah, thanks, Nikita. So she said, is this true? Only when x and y are independent. What's a really common bound that we do to bound the union of two events? So someone mentioned the chain rule. So that's specifically for when you're chaining together probabilities. It's like when you have some event given another event. In this case, we have the union of two events, which is lower bounded by their sum. Or I mean, it is a lower bound for their sum. It's less than or equal to the sum. And this one, I didn't think it would be that instructive to just watch me write all of these out, but I would go through the textbook and make sure you know, like Bernoulli, binomial, geometric. I think those are the three that we use in 251. Just make sure you know what they are, like what they represent, so that if you see them used in a problem, you can be like, oh, I know that. That is a binomial distributed random variable, and I know what its expectation is. So knowing all the common variable distributions and knowing what the expected value for each one of those distributions is. Yeah, so those are like some basic probability stuff that y'all should have down. Okay, so going into the algorithms part of randomized algorithms, knowing the difference between Monte Carlo and Las Vegas algorithms. So when I was in, when we were teaching recitation last time, someone gave this awesome mnemonic, but I didn't get their name because their video is off and they're somewhere down in the Zoom chat. But they gave this really nice mnemonic. If you are that person, you should message me so I can give you credit for this. I really like this. Monte Carlo algorithms start with an M and they might make a mistake because they aren't guaranteed to be correct. Las Vegas algorithms start with an L and they could take a long time, but they don't gamble with correctness. So formally what that means is that for all inputs X, the probability that your Monte Carlo algorithm A is wrong, so in other words, it does not equal the true value of what this function should return, is going to be less than or equal to some error bound. So it could be wrong, but it's a bounded wrongness. And also for all inputs X, the number of steps that your algorithm takes, that is guaranteed to be bounded. So there's, with like probability 1, you know that its runtime is bounded by this. So it might make a mistake, but it's definitely going to end on time. And Las Vegas algorithms are kind of like the opposite, that with probability 1, you know for sure that your algorithm is going to return the correct answer. And as for the runtime, we don't say it just takes like an infinite amount of time. We do have some kind of bound, but it's only an expected bound. So you're kind of gambling with how much time it takes. So the expected number of steps that A of X takes is going to be less than or equal to some bound. So make sure you can recognize when an algorithm is one or the other, that you know the formal definitions and the way the quantifiers are ordered and stuff. And at a really high level, I want to talk about like how you turn one algorithm into another. So for a Monte Carlo algorithm, in like one sentence, can someone say how you turn it into a Las Vegas algorithm? So both of these are exercises in the textbook, turning one into the other. Yeah, awesome. So you just keep running until you get it right. And the reason you can keep running it is because you're turning it into a Las Vegas algorithm, you don't really care how long you take. Well, I shouldn't say it like that. You do care in the expected runtime. So if we ask you to turn a Monte Carlo algorithm into a Las Vegas algorithm with expected runtime blah, it should have expected runtime blah. But so we do care how long it takes, but we don't care for an exact bound. We just need an expected bound. How about the other way around? So right now we have an algorithm that could make a mistake, but, or no, oops, that's the other way around. We have an algorithm that definitely returns the right answer. And now we want to turn it into an algorithm that could be wrong, but its runtime is bounded. Yeah, so this is kind of like the straightforward with the sledgehammer kind of way of doing it. We want to bound its runtime, so well, we just run it for that many steps. If we give you like a big O bound, you can, there's a lot of flexibility here because we're describing these at a super high level. You can like run it for a certain amount of steps, like some multiple of T of X, or if we want a big O bound or something like that. So there's a lot of flexibility and things you should be tweaking there. Okay, so let's move on to what boosting is. So since we're reducing the probability of error, which type of algorithm would this apply to? Monte Carlo or Las Vegas? Yeah, Monte Carlo, which makes sense because Monte Carlos are the ones that have a probability of error. Las Vegas algorithms aren't going to have a probability of error. One thing to note is that unless we specify, unless we say that you can check the veracity of your answer, you don't know whether your algorithm returned the correct answer. So I think someone asked, how can you make sure that your Monte Carlo algorithm is right so that you know how to stop? Unless we say like, oh, you have this verification machine that takes like T of something time to run, you actually don't know. Because if you did know, then who would even care about Monte Carlo and Las Vegas algorithms? You could just be like, I have this verifier. Let me give the verifier yes and see what it returns. And I don't even have to check no, because if the verifier said yes is correct, I'm done. If it said yes is wrong, then the answer is no. You don't even need to do anything randomized. You could just use your verifier. So that makes sense that we usually don't have access to this kind of mystical verifier. So since you don't know if your algo is right. So if you don't know if your algo is right, there's a couple things that kind of help you out. If your algorithm has a particular sided error, you actually do know if it's right under certain conditions. So let's talk about the definition of one-sided versus two-sided error. Another important thing to note is that if we don't tell you whether the algorithm has one-sided or two-sided error, we're normally referring to two-sided bounded error. So, but you still need to know which each one of these are. So if X is a yes instance or if X is a no instance, you're going to have different types of results you're going to get out. So if X is a yes instance, then your algorithm is going to output yes. So it's like guaranteed to get this one right. If X is a no instance, well, then the probability that your algorithm gets that right and actually outputs no, well, it's going to be greater than or equal to some number. I'm just going to write a half as a placeholder, but this can normally be any like 1 minus epsilon that you want it to be. So the probability that A outputs no, it has a good chance of outputting no, but it might also be wrong and output yes. Two-sided error is set it up the same way. If X is a yes instance, if X is a no instance. In this case, both of these are bounded. So actually, instead of writing it out twice, you can kind of write the same thing and just say that the probability that A is correct is greater than or equal to 1/2. So this can get a little bit confusing because you can kind of think of these implications in different ways. One way I like to visualize it, this may or may not be useful for you depending on how you think, but I like to visualize it as if this is like a probability bar, then if X is a yes instance, we know that our algorithm always outputs yes. So if green means yes. And if X is a no instance, well, with greater than 1/2 probability, it outputs no, but there is also a probability that it might output yes. So by drawing it this way, at least for me, it makes it clear that, okay, if our algorithm outputted no, well, then that means I must be in this area, which means X must be a no instance. So when the algorithm outputs no, it's like super confident of its answer because if it says no, the answer must actually be no. If the algorithm says yes, well, now we aren't really sure. That falls into both X is a yes and X is a no category. And we can kind of do this similar thing for two-sided, that if X is a yes instance versus if X is a no instance. In this case, both of our sides are bounded. So if X is a yes instance, you might say yes, but you might also say no. And if X is a no instance, you might say no, but you might also say yes. And this kind of, again, visually displays the idea that regardless of what answer the algorithm gives, like if it says no, you could be in either yes or no. And if it says yes, you could be in either yes or no. So either way, you aren't really sure because the error is two-sided. So with that in mind, also keep in mind that we could add twists to these. We might define our own version of sided error where it's slightly different. But by understanding these, you're more prepared for different twists on it. So with this in mind, how do we boost these different types of algorithms? So boosting both one-sided and two-sided are both exercises in Diderot. So the details and like how you deal with the constants and make sure your runtime is correct and stuff, all of those are in Diderot, but I want to make sure we are all on the same page for high-level stuff. To boost a one-sided error, in general, the strategy for boosting is using repetition. But if you just say, oh, you boost by repeating it, that doesn't really give all the answers. Yeah, you're repeating, but what do you do with those repeated runs? How do you combine your answer? So you do repeat for some number of times. The number of times will depend on how we specify. If we say that the algorithm needs to take this much time or whatnot, whatever constants make the runtime work out. So repeat this much time. You run our initial algorithm, which has one-sided error. And this algorithm is either going to output no or output yes. So based on what we just said, if our algorithm outputs no, what do we know that the answer is going to be? Yeah, we know for a fact that the correct answer then has to be no. So if the algorithm outputs no, we can output no. Our boosted version can output no. If the algorithm outputs yes, we aren't really certain, but we can just repeat. So in other words, this is the part that like goes back to the start of this loop. Yeah, we just continue. I guess that would be the more correct way of writing this, is right, continue, because we wrote repeat twice. But anyways, get the idea. Okay, so the more interesting thing is how do you how do you boost using repetition and if you have two-sided error? So we're going to do the same thing where you repeat for some number of times and you are going to be running our algorithm, but there's no way for us to just break and continue. Yeah, so I think a few people even before had said, we want to take the most common output. So as you're running this, make sure you track all the outputs, count like how many votes do you have for yes, how many votes do you have for no, and then output the most popular one. And this kind of deals with the fact that unless specified, you don't actually know whether A returned the right answer or not. So by outputting the most popular, you don't actually need to know which one's right. You just kind of, you take whichever one's most popular. And with some like pretty high probability, the most popular answer is the right answer. Okay, any questions on that? Sometimes we might put a twist on it and say like, okay, you have some like limited verifier that can tell whether you have the right answer with some probability. So there's a lot of combining these facts together. So the thing I'm trying to hit at here is if you just memorize this, that won't get you very far. But if you understand all the like bits and pieces of it, if we modify it, if we give you a different version, you'll understand how it works and be able to come up with your own analysis. Okay. If it's not 50-50, could you weight the number of occurrences? So when you say it's not 50-50, are you saying that like you got not 50-50 votes for yes and no, or not 50-50 as in not 50-50 over here? Oh, so right here, I guess I drew my picture where it looks like 50-50. We could give you what these bounds are. Maybe it's a really good algorithm that if X is yes, the probability that you output yes is like 99%. I'm just drawing it as 50-50 because it needs to be, it doesn't make sense for your algorithm to be right, like for a binary answer, it's right 1/3 of the time or something less than half. That doesn't really make sense because it's like, well, why don't you just do the opposite of what the algorithm says? If my algorithm is only right 1/3 of the time, then by flipping it, I get an algorithm that's right 2/3 of the time. So this bound could be pretty good, like 99%, 75%, but it's definitely greater than or equal to 1/2. So I just chose the lower bound 1/2, but you'll see in the textbook, it's normally written as like 1 minus epsilon to be more specific. Awesome. So if there's no other questions on this, then kind of like the same thing we did for approximation algorithms, I just wanted to say, like, come up with, like, go through the textbook, make sure you understand why they work, go through the recitation stuff. I would say the analysis for min-cut is pretty involved. You guys had a homework, which is basically like, redo the analysis of min-cut with a slight tweak. And the reason for doing that homework was just so that to force you to go through the analysis of min-cut. It has like all the possible steps that you would need. It has probability in there, it has the chain rule, it has boosting. So just make sure you know all of those steps. I wouldn't say you would have to like do that analysis on the spot. That's like too much to ask in one sitting, but you should understand all of the steps so that if we give you something else that has components of all that, you understand how all those steps work. I'd say max 3 set is just the first one that came to my head. I think it was in recitation, but it kind of hits on a really common thing that shows up in 251, that if you want to come up with a randomized algorithm, like what is your strategy that you should use? Who remembers the strategy we used for max 3 sat? What was our super big brained involved strategy to get the maximum number of clauses satisfied? Yeah, so that is the big brain strategy here for randomized algorithms. Just if you just do the most random thing, at the very, very least, you'll have a good starting point. You might need to make some tweaks to make it a little better, but just by doing the like straightforward random thing, you often get a pretty good bound. So let's do a little warm up. So I said we would do this magnets problem, but before we jump into that, let's do a little warm up. That if you have like an arbitrary, well, you have this bit string and you're trying to find the index of a 1 in there. So it's full of 1s and 0s. Let's just picture this. And you know that it has at least half of its bits as 1s. If you can't see it, so if we like cover this up and then you just get to, oh wow, you can't see that I'm covering it up with my hand. If we covered up this bit string and then you said like, look at index 5, we would uncover that and be like, okay, is this a 1 or a 0? And your goal is to try and find the 1. So what would be a good random strategy based on what we just talked about in the last slide? Yep, just guess. Just pick a random index and guess. And what if it's wrong? What if we uncover it and there's a 0 under there? Yep, you try again with a different random index. So we want to prove, so coming up with random strategies like this isn't too bad. Now the question is, can we prove that it has expected runtime theta of 1? So let's say its actual runtime is t. So this is the number of like unveilings, number of uncoverings that we have to do. So we want to show that the expected value of the number of uncoverings we have to do, this is going to be in theta of 1. So it can be any constant. It doesn't have to be 1 itself. It can be 20, but as long as it's limited by 20. Yeah. So the strategy here is that you could just say this is a geometric distribution, and it has probability the parameter is 1/2. Therefore, the expected number of steps it takes is 2, because I know that if for a geometric random variable, which t is, if it has a probability parameter p, then the expected value is always going to be 1/p. So in this case, p is equal to 1/2. So our expected value is 2, and that gets us theta of 1. Oh yeah, so if you do this a little bit smarter and you remember where you checked and then you don't recheck that again, technically you would be a little bit better, but for the sake of our analysis, we can just even do like a lower bound and be like, okay, well, I know it takes like less than or equal to 2 steps, and that's all I need to show that this is in theta of 1. Another way you could do this if you didn't remember geometric, but this is why I'm saying it's really important that you guys remember your random variables, because if you did, then it's like done, geometric, done with this problem. But if you didn't, one way you could analyze this is that the expected number of time steps it takes is going to be the number of time steps if you found a 0 versus the number of time steps if you found a 1. So you kind of turn this into a recurrence. So I guess this is not 1/2. It's technically greater than or equal to 1/2 because you have, or no, less than or equal to 1/2 because you have at least 1/2 ones. So with 1/2 probability, the thing that you unveiled was a 1, and then you're just done. But with 1/2 probability, the thing you unveiled was a 0, in which case you took the step to unveil it, but you still have to keep going. So if you go ahead and do the math and solve for this, you also get that the, oops, I should write there, that the expected value of t is less than or equal to 2. So these are two different strategies, but the point is that like the more probability skills you're comfortable with, the easier these problems become. Okay, so now let's jump into the magnets problem. So there is quite a bit of reading. So first let's go through this. Magnets, how do they work? So we have some sequence of n magnets, and we want to place them in a display case, and they're numbered 1 through n. And we know that the pth magnet has a specified location. So we can't place it anywhere we want. It has to go into the specified location. But we're only allowed to insert the magnets one at a time, and it costs 1 joule of energy to insert a magnet. Also, I have no idea how physics works. I don't know what this really means. But this is like our setup. It costs 1 joule to insert any magnet, but that's in the regular case. So normally it costs us $1, or 1 joule. I always turn these into dollars in my head. If the magnet happens to be placed in a location such that it becomes part of the closest pair of magnets, then instead of costing 1 joule of energy, it costs I joules of energy, where I is how many magnets are in the display case right now after you place that guy down. So we want to come up with an algorithm that takes O of n time and also costs O of n joules. So I know that was a lot of reading. So let's first kind of digest what's going on in the problem before we can jump into solving it. So here's a little example. If we have, these are our 5 magnets, they have a specified location at which they have to go. We don't get to choose where they go, but we do get to choose what order we put them in. So our algorithm is basically trying to come up with, like, given these 5, like what order should we place them in if we know where their locations are supposed to be. So if we just put them in kind of the order they're given right now, 5, 4, 3, 2, 1, 5 we would have to put here. This costs us 1 joule. So let's keep a counter so far. We have 1. Then I put the 4th magnet down. This one actually forms the smallest pair. So the distance between these two is the smallest out of all distances because it's the only distance so far. So this one costs us 2 joules. So we had 1 from the 5. We have 2 from inserting the 4. So 3 so far. Then we insert 3. Well, actually now this becomes the smallest distance. Because this distance used to be the smallest distance, but now 3 just created the newest smallest distance. So also I lost track of, okay, so 5 costs us 1, 4 costs us 2, 3 costs us 3 joules because it has to pay for the 5, the 4, and itself because it happened to create the closest pair. 2, once we place it down, that one also, what do we do about ties? Does it say? Oh, so ties don't actually penalize us because we have to be strictly shorter than the shortest distance. So in this case, even though this had a distance of 2, 3 and 5 already had a distance of 2 away from each other. So this only costs us 1 joule, so we're safe there. And lastly, if we place this 1, well, once again, that becomes the smallest pair. So that would cost us 5 joules of energy because there's 5 on the board so far. Does everyone get where the numbers are coming for and why it costs this much to place the magnets down? Are there any questions on the problem setup? Because otherwise solving the problem won't make any sense. And if you're wondering what this giant table was, at one point in time, I thought it would be helpful to know the distance between all of these guys, but then I realized it's probably just easier to look at the picture. It doesn't really matter how much bigger one distance is from the other. All that matters is whether you're the smallest or not. So you don't really need to worry about what the exact distances between all these points were. Okay, so let's do a different run of this algorithm, which is a good strategy in general. As you're trying to figure out a problem and come up with strategies for it, is just like run a couple examples to get familiar with the problem setup, and that'll really like prep your mind to be able to come up with a good solution. If we were somehow a little bit smarter about this and we noticed that, okay, 1 and 2 are the closest here. So if I placed 1 down, that cost me 1 unit. So let's do run 2. Cost us 1 unit. Then I place 2 down. Well, that becomes the closest pair between each other. So that's going to cost us 2 units. But now we're done with the closest pair. Nothing else can be the closest pair. So we know that for everything else, 3, 4, and 5, all of these are just going to cost us 1 because there's no way they're going to be able to create the smallest pair because we already got rid of the smallest pair in our first step. So this is +1, +1, +1. So there is some nice structure to this, but we need to come up with an algorithm that can do this in O of n time. What's the issue if we try doing this, where we put the closest pair first, and then we place everything else? Because it does have this nice structure where we pay 1 at the start, we only pay 2 for the second, and then everything else is just +1. We don't ever run into the issue of like, oops, +5. Exactly. Finding out that 1 and 2 are the closest pair, visually we just saw it, but if you're actually given a list of coordinates and you have to try and find out which 2 form the closest pair, you would have to go through all potential pairs of magnets, which would take you n squared time. And we only have O of n time on our hands. So there's no way we can do that. What else could we do? Is there any other way we could arrange these? Maybe we can't find the closest pair. Any strategies that might be good? Okay, I will admit that that was a little bit of a trick question because there's not much you can do in O of n time. You can't sort these guys. Plus, if you were going to sort them, would you sort them by x coordinate or y coordinate? That's kind of like a heuristic for distance, but 2 pairs can be like, or 2 magnets can be very close in x coordinate, but be really far in y coordinate, which would lead you right back to trying to sort them by the distance between each other, pairwise distance. And even if you could just use one distance, sorting already we know takes n log n, and we only have O of n time. So that only really leaves us with one option. Yeah, the coordinates are definitely given. You know where they're supposed to be placed in numbers. Exactly. We don't really have much flexibility here. Just pick a random order. And find the closest one to it. So if we did that, I think that would still turn out to be n squared. It would actually be slightly like a lower n squared than our previous algorithm of finding all pairs, but it would still be O of n squared. Even though it's actually smaller, it's asymptotically the same. So we don't really have much flexibility, so the only thing we can do is just place them in random order. So once again, coming up with the algorithm wasn't so bad. Let's do the analysis of what the cost actually is. So a good starting point is say, let's say our random variable c is the cost. Our goal is to try and figure out what the expected, or not this, our expected cost is something which we're trying to figure out. Our hope is that it's an O of n, but we still need to prove that our expected cost is an O of n. One thing we can do is if we analyze what the cost per step is, the ith cost, it's either going to cost you $1 or 1 joule, I keep saying dollars, or it's going to cost you I joules. So it costs you I joules if this pair, or not if this pair, if this magnet forms a pair, if this magnet forms the closest pair. And this is the otherwise case. I guess I could have written them in a different order. So what does this kind of structure look like when we have two options, this binary thing, and we want to find the expected value of something? What's a good technique we have? Indicator random variables. One thing to notice is that indicator random variables are 1 and 0. So this isn't quite 1 and 0, but we can still use an indicator random variable. So let's say xi is going to be 0 or 1, and it's 1 if ith magnet forms, I spelled magnet wrong, but y'all know what I mean. Closest pair, and this is the else case. So we have this indicator, and somehow we want to use this indicator to get our actual cost. Normally, whenever we want to find these, we can just like sum up the indicators. What's the issue if we sum up our indicators here? What does that end up counting?
Like all the pairs.
Yeah, it counts how many magnets formed the closest pair. How many pairs of closest did we accidentally create? But that's not exactly what we want. We want the cost. And one way to immediately notice this is that we need to include xi somewhere in there along with our indicator. Yeah, Stephen gave a good suggestion, is that if we want to multiply I by xi, then we do get the fact that the cost here is I. But the issue is if we just multiply I by xi, where do we ever get the +1 cost? So we want to have both of those at the same time. So our cost is definitely going to be the sum of something over these indicators. And we do want to add, when this indicator random variable is 1, we do want to add I. But when it's 0, we want to just add 1. So if we wrote it out in English first, so our cost is +1 in one case, and our cost is +I in the other case. And the two cases here are if xi is equal to 0 and if xi is equal to 1. We can't really write if statements inside of our summation, though. Yeah, so one good idea is that if we just multiply, so there's a couple of different ideas. The last couple were really close, but the issue there is that now if you're always adding, oh, never mind, I didn't see the -1 there. Okay, so that is a strategy of writing it out, and that works. More intuitively though, so what you guys did is a simplified version of what I'm going to do, which is I'm just going to replace these ifs with, well, if xi is 1, well then we can just multiply by xi, because multiplying by 1 does nothing. If xi is 0, well, how do I turn the 0 into a 1? I can do 1 minus xi. So this trick right here, it'll simplify to exactly what you guys wrote down, which is 1 plus I minus 1 xi. So you guys went ahead and got the correct answer down there. But intuitively, if you didn't immediately think of it that way, you could split up your if statement into this. And this is like a neat trick of turning your indicator random variable when it's a 0 into a 1. Because when this is 0, this entire thing becomes 1. Okay, does that make sense how we got the summation? I'm seeing some no's. I don't know if that was left over from before or... do people have questions about it? So someone hit no in the participants bubble, but no one asked a question. So I'm going to take it as that was left over from the last question. And those people are probably not by their computers right now. Yeah, so we have the summation. I'm going to go ahead and use your guys' version because it's nice and small, more compact. So the previous version, they both simplify down to this. So either way is fine. So we have this summation, and we want to find the expected value of C. Well, we can bring this 1 out because the 1 doesn't depend on anything, and that just becomes an n outside of the summation. As for the rest of it, we still have the summation of I minus 1 xi. Or, well, we want to take the expected value of that. So using linearity of expectation, we get the expected value of xi. So now the question becomes, what is the expected value of xi? So we know xi is an indicator. So its expected value is just going to be the probability that it's equal to 1. But what is the probability that it's equal to 1? In other words, what is the probability that the ith magnet forms the closest pair? Keeping in mind that the ith magnet is completely uniformly random out of all of our magnets. Yeah, so that's pretty much right. It's off by 1, but because we're doing big O, it wouldn't even show up. So it's actually going to be I minus 1 over I choose 2. So the minus 1 is on the other side. And the reason for that is that when you put the ith magnet down, it pairs up with I minus 1 other magnets. So it doesn't pair up with itself. But overall, there are I choose 2 magnets because you do have to include itself there. So the number of pairs that the ith magnet forms is I minus 1. But the number of pairs on the board in total is I choose 2. And if you simplify it out and do the math, this becomes 2 over I. So putting this into our summation, 2 over I, if you put this into big O, well, the i's kind of cancel out. There is a minus 1 there, but they basically, oh, this is a fraction. They basically cancel out. In terms of big O, the minus 1 doesn't make a difference. So then you would just end up with n plus n, which is 2n, which is of course in big O of n, which is what we wanted to show. Okay, so then we just showed that our randomized algorithm has O of n expected energy cost. This is what we wanted to show. And you would also have to show that its runtime is O of n, which is pretty straightforward because we aren't doing anything other than placing the magnets down. We don't really care what order they're in. So any final thoughts or questions? So we want to answer as many of your questions as we can. Feel free to ask on Didero. We are pretty much right on schedule. So yeah, if you guys need to go, feel free to go. Otherwise, we're just gonna. So someone asked, is there gonna be a big review for the exam? So we're gonna have 3 small reviews. This was one of them. I think Nick is doing another one pretty soon, right? Today?
Yeah, in an hour at 3.
Yeah, so in an hour, Nick is gonna be doing a graphs review. And then tomorrow, Somal is gonna do like an NP and reductions review. So we're gonna have 3 little reviews going over test stuff. Yeah, so we're gonna post a video, and I'm also gonna post this PDF of like the solutions we wrote out.
Let me know if your recording comes through properly so that I can do it right.
I really hope it didn't record like my face talking instead of the screen.